Alright, are you all ready? Good morning, my name is Ben Jackson, and I'm the design team lead for FAST Aerospace Technologies this semester. This is our final design review for the Aurora supersonic transport. For the remainder of the presentation, the screen above me will be referred to as the primary screen, and the screen to your right will be referred to as the secondary screen. I'd like to introduce the Aurora supersonic transport, as was left off by our team in our preliminary design phase. I'd also like to introduce the rest of the team with Jacob Curl, Evan Estep, Mark Miller, Shlik Patel, Trent Martinez, Alex Young, Andre Sandoval, Alex Robertson, Zach Parrish, and Alex Fraga. On the primary screen is a brief overview of what we will be covering in this presentation, including the initial wind tunnel test and results, which was done to validate the predicted performance of our aircraft, and then moving on to a final wind tunnel test and results to validate the impact of model modifications that were made based off of the results of the primary wind tunnel test. On the secondary screen, I'll be going over some of the motivation as to why our team decided to design a supersonic transport. So business and politics both run on face-to-face communication, and advances in long-range communication, such as video conferencing, will never fully be able to replace in-person meetings. Just imagine how different this presentation would be if I were getting it from halfway around the world. Current commercial air travel, whether it's for business meetings, political summits, or just for recreation, currently operates solely in the subsonic regime, and a supersonic transport capable of flying intercontinental routes could reduce flight times by over 50%. Recently, interest in supersonic transports has reemerged in the commercial industry, with NASA awarding Lockheed Martin a $250 million contract earlier this April to assist in the development and research of a potential future supersonic transport. To remain competitive, FAST Aerospace proposes an aircraft with a maximum range that is unseen in supersonic transports, both past and proposed. On the primary screen is a comparison between the predicted performance of the Aurora and other supersonic transports, including the Concorde, and a recent development in supersonic transports, Boom SST, which is currently in development. You will note that the predicted range for the Aurora is nearly double that of Concorde. And also worth noting is that while the Boom SST and the Aurora have the same predicted cruise Mach number, the predicted flight time from JFK to London Heathrow of the Aurora is slightly less than Boom, as it is predicted that the Aurora will be able to reach Mach 2.2 earlier in the cruise phase, allowing for a faster average flight speed. On the secondary screen is a similar comparison between the predicted performance of the Aurora and other commercial aircraft, including the 747 and 787. Note that the Aurora's range matches the range of these wide-body aircraft, and please note the drastically reduced flight time. I'd now like to introduce Alex Fraga, who will be going over our mission specification and profile.
Thank you, Mr. Jackson. Our mission specifications are derived from our project's request for proposal, or RFP. Our RFP dictates that we must be range capable to fly 3 key mission routes. These 3 key mission routes are visually represented on the world map on the secondary screen. It's also important to note that of these 3 key mission routes, the most significant route is from LAX to Sydney, as it has the longest range of 7,500 nautical miles. Our aircraft also must be capable of supercruise at a speed of Mach 2.2 while carrying 80 passengers, 2 pilots, and other essential crew members, as well as 50 pounds of baggage for each and every person on board. RFP further dictates it must be operable from a 10,000-foot runway while meeting all size and weight requirements to be compatible with current airport infrastructure. Lastly, our aircraft must comply with all CFR and ICAO requirements, which include using a CFR Part 33 certified engine. The Aurora's mission profile is similar to that of current transport aircraft. It begins at the departing terminal with an engine startup procedure, followed by a taxi out to a runway of at least 10,000 feet. At the runway, the Aurora will take off while being sure to obtain a ground clearance of at least 35 feet to avoid any obstacles that it may encounter. After the Aurora takes off, it will climb to an altitude of 40,000 feet while it will begin its cruise phase. For the Aurora's cruise phase, it will maintain an altitude of 40,000 feet while accelerating to a speed of Mach 2.2. As fuel weight is burned and specific excess power is increased, the Aurora will continuously climb to an altitude of 58,000 feet. Once the Aurora reaches an altitude of 58,000 feet, it will maintain this altitude as well as speed of Mach 2.2 for the remainder of the cruise phase. At the end of the cruise phase, the Aurora will descend, following an approach to the landing runway, where it will then land, taxi in to its arriving terminal, and conclude with an engine shutdown procedure. I'd now like to introduce Evan Estep, who will be covering the Aurora's structural model.
Thank you, Mr. Fraga. In addition to the wind tunnel data that will be discussed later in this presentation, a structural model for the Aurora was also designed based on the aircraft as it was left off in preliminary design. The primary screen shows the structural model of the wing, which will be constructed from a quasi-isotropic laminate of carbon fiber. In this context, quasi-isotropic refers to the fact that the laminate includes a symmetric distribution of 0, 90, and plus or minus 45-degree plies, such that the laminate behaves the same in both principal axes. The wing construction consists of spars, ribs, and a load-bearing skin that's common in composite aircraft construction. Additionally, there are certain ribs removed to allow for the storage of landing gear and additional fuel tanks. This factor has been considered in the computational analysis of the wing structure. The secondary screen shows the loading information for the wing. The CFR mandated load factor of 2.5 combined with the aerospace standard factor of safety of 1.5 and the aircraft's maximum gross takeoff weight of nearly 540,000 pounds produces an ultimate load of just over 1 million pounds per wing. The primary screen now shows the results of the analysis of stress occurring on the wing. The wing was modeled with the entire root being clamped in place and thus treated as a cantilever beam. The maximum stresses in both compression and tension occur at the root of the aftmost spar, and both of these are within the allowables for carbon fiber. The secondary screen shows the wingtip deflection occurring under the maximum load. The maximum wingtip deflection of 3.37 feet, or just over 40 inches, occurs at the wingtip as expected, and is approximately 7% of the aircraft's half span of 47.5 feet. Though no strict requirement of wingtip deflection was enforced, this value of 7% was determined to be acceptable. The horizontal tail was modeled using the same material properties for the main construction of the horizontal tail as the wing. Additionally, because the horizontal tail is all moving, it includes a titanium rotation pin placed at the quarter cord of the horizontal tail. The horizontal tail also uses the same construction of ribs, spars, and skin. The secondary screen shows the loading data that was used for the analysis of the horizontal tail, which includes the same factor of safety of 1.5 and CFR mandated load factor of 2.5 Gs. The maximum load of the horizontal tail was determined to be in place during takeoff, where the horizontal tail sees its maximum deflection. The horizontal tail analysis was broken into two primary components. The first component is intended to isolate what's occurring within the titanium rotation pin, which is what is shown on the primary screen. The stress on the titanium pin is shown to be at its maximum along the bottom side of the pin, where the surface is in tension, and this value is within the allowables for titanium. The secondary screen shows the deflection analysis done on the titanium pin. The deflection at the end of the pin is approximately 1/10 of an inch, and it is approximately 7% of the aircraft's half span of 47.5 feet. Though no strict requirement of wingtip deflection was enforced, this value is within the allowables for titanium. The secondary screen shows the loading information for the wing. The secondary screen shows the loading data that was used for the analysis of the horizontal tail, which includes a Because of this small value, it was determined that the deflection of the pin was not a significant factor in the remainder of the horizontal tail analysis. The second component of the horizontal tail analysis required fixing the entirety of the wing root of the horizontal tail root, and again treating it as a cantilever beam. The maximum stress in tension and compression again occurs at the root of the aftmost spar, and both of these values are within the allowables for the same carbon fiber laminate. The secondary screen shows the effects of the load on deflection of the horizontal tail. The deflection of the horizontal tail maximizes at just under 6 inches. This value is less than 5% of the horizontal tail's half span of 13 feet, and thus was also determined to be an acceptable value. The primary screen now shows an overview for the entire aircraft structure. The fuselage structure consists of circular bulkheads and stringers that run the length of the entire aircraft. The secondary screen also shows the sea level flight envelope for the Aurora with its CFR mandated maximum and minimum load factors of 2.5 Gs and -1 Gs respectively. At this time, I would now like to introduce Jacob Curl for wind tunnel and testing.
Thank you, Mr. Estep. So the wind tunnel visible from the primary screen of our presentation is where we conducted our testing. This is in the Nancy and Tracy Doryland Wind Tunnel facility. Shown in the secondary slide are our information for maximum velocity as well as the cross-section. But visible from the primary screen, we have several points of note, including the computer at which we collected our data, the balance at which we attached our aircraft model, and then locations 1 and 2, which are designated as the points at which we took pictures, not only for flow visualization, but also for model adjustment confirmations. The flow visualization conducted for this test consisted of tufts that were attached using tape strips. The primary screen shows flow visualization from the bottom of our aircraft. This flow visualization allowed not only for detection of flow direction, but also flow separation as well. Now on the primary screen, what we have is the pyramidal balance for our wind tunnel testing. This balance has 6 points of measurement in total. We, as a team, decided on a maximum load of 40 pounds, which includes a factor of safety from the capabilities of this balance. And then the 2 changes or the 2 adjustments made to the model during testing included adjustments in angle of attack as well as beta angle, which were adjusted via the use of a motor, which could automatically adjust our angle of attack, and a rotating plate at the base of our balance, which could be used for adjusting beta angle. I would now like to introduce Trent Martinez for wind tunnel model.
Thank you, Mr. Curl. On the primary screen above me, you will see a dimension drawing of a 1/90th scale wind tunnel model. The scaling factor was derived using the constraints listed on the secondary screen. The constraint that determined our scaling factor is going to be the interference of our wind tunnel model with the wall effects. You can also see the model on the table sitting to my left. The majority of our wind tunnel model is comprised of 3D printed parts. These parts include 3 fuselage sections, 2 different tail configurations. One is going to be a clean tail cone. The other one is going to be the tail with the vertical and horizontal lifting surfaces. We also have printed the left and right strake, left and right wing, and left and right engine pods. On the secondary screen, you will see a list of the materials used for our internal support structure. The majority of our internal support structure is made up of 3 1/8-inch thick steel plates cut to the plan form shown. These steel plates are designed to structurally support our wing, strake, fuselage, and add an attachment point to the pyramidal balance. We also use 1/8-inch thick steel rods, which were used to secure the fuselage sections to the main support plate, and 1/16-inch thick steel rods, which were used for additional support for the wing and the strake. Once we received our 3D printed parts, we proceeded to sand, prime, and paint them to achieve a smooth surface finish. For parts that were too thin to house an internal support structure, we did a fiberglass epoxy layup to strengthen them. Our steel parts were cut on a water jet, so when we received them, we simply deburred them and tapped them in the appropriate locations for model assembly. Now on the primary screen, you will see a short video which will detail the assembly procedure for our wind tunnel model. We first start by epoxying the wing, strake, engine pods, and 1/16 inch support rods together. We then proceed by sliding on each fuselage section and securing them with a 1/8 inch thick steel rod going through the nose and the tail. Once that is complete, we will slide on the wing and strake support plates going through the fuselage and will interface with the main support plate. We'll then install the wing and strake combination onto their support plates and secure them with screws. We will also assemble the pyramidal balance mount and will install underneath the fuselage and screw into the main support plate. On the secondary screen, you can see a ghost view of how the model is fully assembled and how the interfacing parts are all together. In order to get our static stability derivatives for our wind tunnel test, we found the CG locations of both our physical model and of our airplane at 1/90th scale. Both of these CG locations are shown on the primary screen above me, with the most apt location is going to be that of the physical model. These CG locations are also shown on the secondary screen as measurements from both the nose of the aircraft and from the pivot point of the pyramidal balance. I'd like to now introduce Shlok Patel, who will be going over the aerodynamic data for our initial set of wind tunnel testing.
Thank you, Mr. Martinez. First, let's go over what model test configurations we had for our initial test, as well as what sort of tests we gave up for the initial wind tunnel test. First, on the primary screen behind me, you can see the 3 different configurations that we had for our initial wind tunnel test. First, we have the complete aircraft, which is obviously the aircraft with its wings, fuselage, and tail. And then the clean tail cone, which is the aircraft with just the wings and the fuselage, and then fuselage only, which is always self-explanatory, just the fuselage. On the secondary screen, you can see what tests we ran for those 3 different configurations. The variables that we ran the tests on were the angle of attack and the side slip angle. One was held constant, while the other was varied. For angle of attack, we varied from -4 degrees to 24 degrees, while beta angle, we varied from 0 degrees to -10 degrees. And those are ran on the 3 configurations. Moving on to the data that we retrieved from the tests. Starting off on the primary screen behind me, you can see the lift curves. And in the gray, it was original airfoil data, and the other 2 curves are for our wing, predicted data we got from our preliminary design phase, and then the red dots being the experimental data that we got from our initial wind tunnel test. On the secondary screen, you can see the important values that we gained from the initial wind tunnel test, such as CL alpha, CL max, and then alpha stall. Moving on to stability derivatives. For all 3 stability derivatives, what's important to note is that the solid blue line will be the predicted data that we got from our preliminary design phase, and then the red dots and the trend line will be for the data from the initial wind tunnel test. Starting off with longitudinal stability. You can see for the most part that the data that we got from the initial wind tunnel test followed in terms of slope of our predicted data, with the exception of near 10 degrees angle of attack, we have a slight region of instability. On the secondary screen, you can see the values of CM alpha in per degrees, as well as the difference between the overall trend from predicted data to wind tunnel data. Moving on to directional stability. Same thing applies. Visually, you can see in both slope that our predicted data and our wind tunnel data relatively agree with each other, and the values are calculated for CN beta and the difference between them, and showed both positive. Finally, lateral stability. You can see once again visually on the primary screen that they're both negative slopes, and that the trend line relatively stuck close to the predicted data, and as on the secondary screen with the CL beta values both being negative and relatively close to each other. Now I'd like to introduce Mark Miller, who will be going over initial data results as well as modifications.
Thank you, Mr. Patel. A summary of the initial wind tunnel data is tabulated on the primary screen. What's noted is the parasitic drag, which is higher than predicted. This is due to the difficulty in accurately predicting the parasitic drag from empirical methods and from limitations in the wind tunnel due to flow-through inlets, mount interference, and interference between the individual components. Also what's noted is the lift curve slope, which correlates very closely with the predicted value. Finally, the initial data indicates that the aircraft is stable along each axis, with slightly lower stability along the longitudinal and directional axes, and slightly higher stability along the lateral axis. Now moving on to the data results. From the data revealed a region of instability from approximately 6 to 12 degrees along the longitudinal axis, which was determined at the horizontal tail ASA partial contributor. Also, the data revealed that the aircraft is still stable along the lateral and directional axis. Now, again, as previously stated, accurately predicting the parasitic drag is very difficult. As shown on the secondary screen, are the model modifications that resulted from the initial wind tunnel test. The first and most significant modification was to modify the wing from a crank delta wing platform to a conventional delta wing. This was done to eliminate any possible wing strake interference, which is also a possible contributor to the region of instability. The second modification was to increase the incidence angle of the horizontal tail from 0 to 7 degrees. This was done to also attempt to minimize this region of instability. Now I'd like to introduce Zachary Paris to discuss the final wind tunnel model.
Thank you, Mr. Miller. On the primary screen above you can see the modifications to the model, and you can see the difference between the original model and the modified. The two differences, again, being the change in the platform from a crank delta to a conventional delta, as well as a change in the horizontal tail from a 0-degree incidence to a 7-degree incidence. On the secondary screen, you can see a 3-view drawing for the modified model and its dimensions. On the primary screen above me, you can see the difference between the crank delta and the conventional. The root cord being the same at the fuselage between both planforms, as well as the span being kept constant. And then on the secondary screen, the change in the empennage from a 0-degree incidence to 7 degrees. On the primary screen, you can see the internal structure for the modified wing. The modified wing used the same mounting locations as well as the same internal structure as the original wing. These parts were also 3D printed here at Aurora in the REF prototyping lab. They were sanded after receiving them from the REF prototyping lab for smoothness, and then fiberglassed, and then resanded. Once resanded, they were again primed, painted, and attached to the model. At this time, I would like to introduce Alex Robertson to go over our final wind tunnel data.
All right, thank you, Mr. Parrish. Good morning, everyone. So for our final data analysis in the wind tunnel, it was used to validate the implications of our model modification. And to start off that data comparison is going to be our lift curve. So shown on the primary screen are the two configurations for our horizontal tail, and the modifications have very little impact on our total aircraft lift. Therefore, the two lines are going to fall almost directly on top of one another, and you may not be able to distinguish them individually. So getting into the data, the solid blue line represents our predicted aircraft data, and the red data set represents the old wing and old tail configuration, which is from our initial wind tunnel test, both of which you saw earlier. Now the yellow data set represents the old wing with the new tail configuration. The green set represents the new wing and old tail configuration. And finally, the gray set represents the new wing and new tail configuration. This color scheme and order will be used for the next 3 slides of presented data. So from this data plot, we can see that the new wing produces more lift at each angle of attack, as well as the nonlinear region where we start to see vortex lift at those higher angles of attack. Shown on the secondary screen are the derivatives CL alpha of the linear region, as well as the maximum values obtained at the angle of attack at 24 degrees. So moving on to our longitudinal stability data. When comparing the original model, which is represented by the red line, to that with only modifying the tail, represented the yellow line, we do see that this modification does reduce our region of instability around that 10-degree mark. However, with an all-moving horizontal tail, we do not think this fix will be sufficient. So when looking at the new wing, we clearly see that it is unstable. However, this is only due to utilizing the same fuselage interface as the old wing, which puts the new aerodynamic center forward of the model's center of gravity. Now, if I can direct your attention to the angle of attack where we first saw that region of instability, around 10 degrees, the new wing does not have the increase in pitch-up moment as the old wing. Instead, this now happens at around 15 degrees, which is beyond any angle of attack we would see in flight. On the secondary screen are the stability derivative approximations obtained from linear trend lines fit through each data set. And we see relatively similar magnitudes for each. All right, moving on to our responses to side slip angle, starting off with the yawing moment. Unfortunately, we saw some data acquisition issues at -10 and -2 degrees. -10 and -2 degrees. Now, the left side of the plot on the primary screen is representative of the data points that we collected because we tested negative beta angles. The right side of the plot represents the trend lines fit through each data set, slope of those lines, forecasted out starting from the origin. So, the zero yawing moment we see at -10 degrees in beta angle is highly unlikely because that is our maximum beta angle. And the odd jump from negative to positive also indicates that this data is likely an anomaly, which does impact the stability derivative represented by that green line. Again, shown on the secondary screen are the stability derivatives we obtained from those trend lines. And we do see that the Aurora is stable for all configurations. Finally, we have the rolling moment response to side slip. Now, in this case, we see those data acquisition issues again, however, this time at an enormous magnitude. On the previous plot, our vertical axis maximums were at 0.1. However, in this case, that would completely cut out the data point at -2 degrees. But if you look closely, the Aurora is still showing stable for all of the trend lines forecasted out on the right side of the plot, with the exception of the green line. However, this is only due to collecting a data point at over 10 times the magnitude as expected, which we do believe is caused by that anomaly. Once more, shown on the secondary screen are the stability derivatives obtained from those trend lines, and we do see that the Aurora is stable for all remaining configurations. And now I'd like to introduce Andre Sandoval, head of aircraft performance.
Thank you, Mr. Robertson. The following performance parameters were obtained by using data collected from wind tunnel testing. Now, note that the initial test performance was obtained using data from our first round of wind tunnel testing, and final test results was obtained using aerodynamic data from our second round of wind tunnel testing with our modified wing. Note that at this time we have not completed any actual flight testing, and that all data will be compared to predicted performance from the aircraft preliminary design phase. Starting with takeoff, assuming a takeoff weight of just under 540,000 pounds and a density altitude of 5,000 feet for a field length margin, the predicted initial test and final test takeoff distances are tabulated on the primary screen. Note that this includes a ground roll, transition, and climb out to 35 feet as required by CFR Part 25. Moving on to thrust required and thrust available. The thrust required and thrust available plot for maximum takeoff weight at sea level is shown on the primary screen, and the thrust required and thrust available plot for at 40,000 feet, which is where the Aurora will begin its cruise, at a post-climb weight of 490,000 pounds is shown on the secondary screen. Because the Aurora has such a large fuel fraction, it is important to see how the aircraft will perform toward the end of its cruise once it's burned a lot of its fuel. So on the primary screen, you'll see thrust required and thrust available plot at a end of cruise weight of 315,000 pounds at 50,000 feet. Note that at these conditions, using data from our initial wind tunnel test, the Aurora can reach Mach 1.8, and data from our second round of wind tunnel testing show that the Aurora can reach about Mach 1.6, about 1.5. These Mach numbers are lower than those that the Aurora is capable of at 40,000 feet at the beginning of cruise. So these Mach numbers were used for the range estimates. And on the secondary screen is an overview for the following slides that are going to show specific excess power. We will start with specific excess power for maximum takeoff weight, and we'll move on to specific excess power at an end of cruise weight of 315,000 pounds. On the primary screen will be the specific excess power using results from test data, and the secondary screen will be specific excess power using predicted data from aircraft preliminary design phase. On the primary screen is the specific excess power plot at maximum takeoff weight using data from our initial wind tunnel test. And on the secondary screen is the specific excess power plot that is predicted from our aircraft preliminary design phase at the same weight for comparison. Now, on the primary screen is the specific excess power plot for maximum takeoff weight, but this time using data from our second round of wind tunnel testing. And on the secondary screen is the predicted specific excess power plot, again from our aircraft preliminary design phase. Now we'll be moving on to the end of cruise weight specific excess power plots. On the primary screen, you'll see the specific excess power plot for an end of cruise weight using data from our initial wind tunnel test. And on the secondary screen, you will see the corresponding predicted specific excess power at the same weight. And now finally, on the primary screen, you'll see a specific excess power plot, again at the end of cruise weight, and this time our second round, using data from our second round of wind tunnel testing, and the corresponding predicted specific excess power plot from our preliminary design. Moving on to range, using almost 300,000 pounds of fuel and a constant Mach number, the ranges for all three cases are tabulated on the primary screen. And now finally, for landing distance, assuming maximum takeoff weight in case the aircraft must land right after takeoff for whatever reason, may be an emergency, and a density altitude of again 5,000 feet for our field length margin, and this time using 900 pounds of thrust reverser. The landing distances for all three cases are tabulated in the primary screen. Note that these distances include a ground roll, transition, and descent from 50 feet this time as per CFR 125 subpart B. And with that, I would like to introduce Alex Young to go over the impact of our test and evaluation phase on our requirements.
Thank you, Mr. Sandoval. From our final wind tunnel test results, it was found that the conventional delta wing configuration shifts the nonlinearity and our pitch stability outside of the angle of attack region that would be experienced by the Aurora. It was also seen from the increase in the incidence angle of the horizontal tail that the downwash from the wing onto the horizontal tail was increasing the pitching up moment, causing the instability, or making the instability worse. It was also seen that the conventional delta wing configurations had an increased CD0 and overall drag when compared to the initial wind tunnel test model. Going forward, FAST has selected the conventional delta wing for its flight test model, as the conventional delta wing shifts the nonlinearity and pitch stability outside of the flight regime of the Aurora. FAST did not select the increase in the incidence angle of the horizontal tail, as the increase in the incidence angle did not fix the instability for pitch. Going forward with the conventional delta wing, the aerodynamic center of the aircraft shifts forward significantly. In order to retain a positive stack margin, the center of mass must also be shifted forward. Due to the increased thickness of this new conventional delta wing, there's more space in the forward part of the wing for fuel. This shifts our center of mass forward enough to give a positive stack margin. However, shifting that center of mass forward gives the center of mass a larger moment arm with respect to the landing gear, giving issues with takeoff rotation. In order to rotate on takeoff, the horizontal tail was resized to 800 square feet. This allows the Aurora to rotate and take off. When comparing the Aurora to past and present competition, the Aurora is able to fly farther than any past or present supersonic transport, and when compared to currently proposed supersonic transports, the Aurora is capable of carrying more passengers. When comparing the Aurora to specifications in the RFP, the Aurora is currently unable to meet three of these. First being the field length of 10,000 feet due to our extended takeoff run. Second being the range, and third being the cruising Mach number. However, these performance parameters will be recalculated with accurate drag data from flight test model. On the primary screen, you can see a rendering of the Aurora with its resized horizontal tail. And on the secondary screen, you can see a rendered isometric view of the flight test model configuration. I'll now like to introduce Ben Jackson for market analysis, labor accounting, and conclusions and recommendations.
Thank you, Mr. Young. On the primary screen is a market analysis for the Aurora, including an acquisition cost and predicted estimates for ticket pricing. The estimated unit cost for the Aurora is just under $400 million, and ticket pricing estimates for both a JFK to London Heathrow route as well as an LA to Tokyo route are similar in comparison to Boom's estimates, and are drastically reduced from first class price cost for current commercial airlines. On the secondary screen, you can see the total hours accrued by the team plotted against the recommended hours, which account for 2 hours spent outside of class for every 1 hour spent inside of class. This works out to 16 hours in total per member per week. Currently, the team has accrued just under 2,400 hours this semester. On the primary screen is a breakdown of this total hour based on category, with the primary contributor being professional development. Professional development accounts for any time spent in class, as well as any time spent researching data analysis tools. And on the secondary screen is a cost estimation based on this hour breakdown, with engineering accounting for the largest portion. In conclusion, FAST has selected a conventional delta planform in order to shift the non-linear region in the longitudinal stability outside of the operational flight regime of the Aurora. The new conventional delta wing has an increased wing area, which has shifted the aerodynamic center of the entire aircraft forward, resulting in a negative static margin, which was seen from our second round of wind tunnel testing. Additionally, the experimental drag was significantly higher than what was predicted for the aircraft, and as discussed previously, this may be an overrepresentation due to limitations of the experimental data. Moving forward, FAST Aerospace recommends shifting fuel tanks into the forward section of the new wing in order to move the center of gravity of the aircraft forward, increasing the static margin. However, this results in a larger moment arm between the center of gravity and the main landing gear, and to meet takeoff rotation requirements, as well as to shift the aerodynamic center of the entire aircraft rearward, FAST Aerospace recommends resizing the horizontal tail to 800 square feet. Finally, FAST Aerospace recommends flight testing to validate the performance of the aircraft and to develop a more accurate drag model. At this point in time, and on behalf of the entire team, I'd like to thank you for your time and open the floor to any questions.
Start over here this time.
First, I want to say you guys did a great job. It's obvious you guys have put a lot of work into this project. You had fun with it, it seems, and created something really unique. So I want to say thank you. First question I have is, I didn't hear anything about what flight conditions you were testing with the wind tunnel model. A lot of this was all about the wind tunnel model, but I didn't see that tied back into your flight regimes and what you were trying to test and verify there.
So based off of an aeroelastic flutter test, the maximum wind tunnel velocity that was used for testing was set at 124 feet per second. And that was what our experimental data was based off of. And again, using Tufts was used to trip the boundary layer for turbulent flow effects.
I guess what I'm asking is I assume this is takeoff conditions you're trying to simulate because you want the supersonic.
Correct, yes.
And how does your wind tunnel conditions compare to your actual takeoff conditions?
I'll refer to Honor Sandoval.
So obviously we weren't able to match Reynolds number. We ran it at about a Reynolds number of 380,000, while our takeoff Reynolds number is in the millions. Mostly it was for stability. We want to make sure that if we are going to make a test model, that it is going to be stable and not something that the pilot can't handle.
And the last thing on that is you saw your stability discontinuity, if you will, the bubble in your CM. Do you think that is related to Reynolds number, and is that a flow regime effect? And would it be there in the flight scale model?
So based off of our wind tunnel tests and our flow visualization, we were not able to pinpoint exactly what was causing this nonlinear region. However, testing between our full aircraft configuration and our clean tail cone configuration showed that the wing body did have this nonlinear region. However, the tail is actually making it significantly worse. So testing between our first set of wind tunnel tests and our second with the increased incidence in the horizontal tail showed that the increase in incidence lessened this effect from the horizontal tail, which indicated to us that there was a significant factor from downwash off of the main wing onto the horizontal tail.
Great job. I'm kind of a history buff, probably because I wrote it. Comparing your vehicle to other vehicles, and so I'm going to assume since all your emissions are over water, you're not trying to reduce burden.
Correct.
So looking at other supersonic aircraft that fly in the region that you want to fly, how big are their horizontal tails compared to yours?
So Concorde has a tailless design, as does Boom, and I believe the Tupolev 144 also has a tailless design with mustache canards for takeoff and landing.
In 102, 106, tailless designs? So there may be a reason for this pattern. So I think you're hurting yourself. I'm going to almost guess that you're going to have a fly-by-wire system on this vehicle. So what I would care about is, do I have controllability?
Right.
Not necessarily just stability. So the question would be, can I solve, using controllability, that issue with the CM?
Right. We did look into a tailless design in prelim, and based off of our analysis and our current understanding of what we could research at that time in the tailless aircraft, we weren't able to make it work, and so the horizontal tail was added for that.
The horizontal tail is a massive piece of drag. If you don't have to have one, don't. So look at the B2s. They want to fly a long way. Okay. So something to take into consideration. So that little CM bump doesn't scare me at all. But I would love to have seen where your CG and your AC were.
Okay.
So even if it's on that 3D plot at the very beginning, those would be really important things for us to understand how you came up with your design. And then the other one I saw was kind of in the structures. Was it just a drawing anomaly, or do you not have a wing carry through?
It was just a drawing anomaly to better show the fuselage structure. Because the main wing does have an incidence angle set to it in order to reduce trim drag in supersonic flight. And so part of the straight portion of that wing would end up being upper towards the passenger cabin, so that area would not have a carry through. But that would have lower loads on it, so it's not a primary concern. But it was just a drawing anomaly to show the fuselage structure better. The main portion of the wing would have a carry
Because I would have assumed that I was looking for that structure to go through so I could attach my gear to it.
Yes,
Wow.
exactly.
So, all right, great job.
Thank you.
Nicely done, guys. Pretty cool looking model right there. First thing I'm gonna hammer down is what Dr. Ashworth told us. Put your axes on there. I didn't see your XYZs anywhere at all. So you define alphas and betas. I have no idea what's positive and what's negative. So that's the first thing. Second thing, you talked about 50-pound bags. What if everyone wants to carry 2 bags?
So I believe CFR actually requires 3.
What?
CFR requires
I think that's part 50, but we accounted for weight and passengers.
3. So that was based off of FAA and CFR requirements.
Yeah. Okay. Good. And the other thing, there's a reason. The 10,000 feet runway, right? That requirement is based on single engine takeoff distances. So hopefully, when you guys did your comparison, you used single engine values because I couldn't see any engine information, so I wasn't sure what the thrust values were, where those came from, and things like that. So just FYI. And then the other one on slide 38, when you compare the old and new, it would be really nice if you used the same colors for what's staying the same, because your horizontal tails changed and the colors are the same, so I was gonna, wasn't sure what was going on there. And then maybe some explanation on where you came up with that 7-degree incidence. Just, just talk it through kind of deal. And wherever you have differences between new or old, or predicted or new, old, have some percentage values instead of just throwing the values up there. Because then I'll have to do the math to figure out how different it is. And just from a flight test perspective, for landing performance in slide 55, maybe talk about what your landing speeds were. Was it 1.23 VSR? And if it was, what it was. That way we can see if your tires can handle it, because that's one of the limitations. But yeah, other than that, really well done.
Thank you.
There you go, that. Nice job, guys. Are those engine pods flow through or are they sealed?
Pardon?
Are those engine pods on there, are they flow through or are they flow through?
They're flow through.
Okay, good. That's the more conventional way to do some of the low speed stuff. You're dealing with a very small scale model. That's something you just don't correct for. How can you rationalize using this wind tunnel data to validate your high speed aircraft performance?
So currently we used our subsonic wind tunnel data to validate, again, our takeoff and landing, which in terms of stability is a very critical phase of flight. And we estimated our wave drag based off of our updates in CD not. Does that make sense?
So you did have a wave drag performance that you improved in those performance measures. Put that up there.
Okay.
That is a hugely important piece of information that you just left out. That's a good thing to do. But then leading into your recommendation that says you validate your performance with flight test data, do you really feel like you're ready to go from here to flight test? Should there be some steps along the way?
Especially with the new horizontal tail, and we'd want to look more into how that impacts the rest of our aircraft performance, and whatever else this new wing could change.
So recommendation for evolution of the test program way before you even get to that flight test. You mentioned that this was used to validate your takeoff and landing performance. You don't have any deployable control surfaces, flap settings, things of the nature. So that would be one of the immediate next steps would be to do a larger scale, low speed wind tunnel model, one of the commercially available tunnels in like an 8x10 test section or something of the nature with deployable control surfaces so that you can actually do things like that, do ground planes for ground effect types of things. Then you move into something more like a transonic model with the same types of things so that you understand the averaging, and then you move into probably about that scalage for a supersonic pig model way before you get to any kind of flight testing.
Right. For the purposes of this class, we were just simulating preliminary design being purely theoretical, and then, purely predicted, and then this phase ending our DT&E.
Yep, I totally understand that. It's just the recommendation is a little bit far-fetching.
Okay.
What the next steps are. One other question. Slide 12B, you did your load cases based on a 2.5G pole. Were any other load cases considered?
No, it was just a 2.5G maximum load factor.
Okay. Just a point there is the 2.5G is critical for some parts of the airplane, but not all. Typically, it's not a critical case for the horizontal tail design. It's something more along the lines of an abrupt pitching maneuver, and gust cases are very important for anywhere along these large types of things.
Okay.
Nice work, guys.
Thank you.
Yeah, great job, guys. I guess the main thing that I have questions on is that you briefly talk about in your initial wind tunnel test the drag, and then you go to your finalized wind tunnel test data, and there's no drag discussion at all. Then all of a sudden we hit this with the range and your thrust, and there's all of a sudden, oh wow, this drag problem. So I think that would have been really important to call that out, at least show it, because then you can walk us through the rest of it of like why everything else happened, instead of just being like, well, holy cow, there's drag, right? It's not what we expected, because then you mentioned it throughout the rest of the presentation, but it's not shown at all. So I mean, just that right there could help you a lot, at least discussing it so you can figure out what to do next.
Okay.
And then when you could go back through testing or whatever, that's how you can fix that problem.
Awesome. All right. Once again, this is really cool to see the progression from prelim to here we are. So just a couple questions that I wanted to kind of ask on 44. So you suggested that the -10 beta was probably an error. Do you have any data to support that suggestion, or why do you think you can say that?
So the best explanation we have for this, because during testing we did not have live data feed from our stability derivatives, so we really didn't see this until after we compiled our results. So the new wing and with the old tail and the new wing with the new tail we would expect to have reasonably similar stability, and what we're seeing here just clearly is not.
Okay, so what you're saying is you were expecting that your new test article was going to have the same performance as the old test article, and the difference was not expected, therefore you're kind of not likely to believe it? Is that?
Between the new wing with the old tail and the new wing with the new tail.
Yeah.
And so we do have indicated stability with the new tail, I believe.
Okay, I understand. So what I'm getting at is, well, I guess let me ask this. Is there any possible explanation that actually is real data?
I'll refer to Mr. Robertson.
So what I would like to drive home is the modification of the tail at only changing the incidence angle should not have had an effect like we're seeing between the green line and the gray line. So that's what leads us to believe it's an anomaly.
Sure, okay, and thank you. That helps me. It would have been, I think that's probably the biggest thing, is make sure that you can walk people down when you're going to throw out data points, have reasons, have data to support throwing out data.
Absolutely. If you do look closely, you also see those 3 data points that do have a little bit of a trend, and then they line up along with the 0 beta angle as well.
Sure.
But we weren't about to throw out data points as you suggested.
Yeah,
Or
yeah,
not suggested,
okay.
sorry, mentioned.
Good. Cool. As far as, let's go to 42. I'll hit on this real quick, and then we'll talk one more thing in 31, 33. What is this prediction? What configuration is the prediction?
This was for whole aircraft.
Right, but there are 4 other cases that you have, so what prediction is this of?
Okay, yeah, sorry. So predicted was from preliminary design, and so so that's old wing, old tail, and then the red data set is the experimental validation of the predicted.
Got it, okay. So if you wanted to, I suspect that you probably could have rerun the numbers each time and had a new prediction each time.
Correct.
Right, so be really careful about just saying predicted with no explanation, because we can run lots of predictions. In fact, it's usually pretty easy to just, change the numbers and hit go on the predictomatic or whatever. Cool. One other kind of thing, 31, 32, 33. Right, so this is fine. Actually, let's go to 32. Yeah, let's go with this one better. So I see you've got a data point at -10, a data point at 0, and then your line keeps going beyond -10, and it goes well beyond 0. Be really careful about extrapolation of data. If you're trying to show actual experimental data, then don't go beyond the ends of where you've been. There's even somewhat of an assumption in drawing a line between those data points, because you're assuming that there's a linear relationship there. In this case, there probably is, but you got to be really careful about that whole extrapolation versus interpolation thing, because it's really tempting to extrapolate. It saves an immense amount of test money, but unfortunately, you can't really do that. You don't have the curve well characterized. So, thank you so much.
Yeah, I'd like to emphasize, fantastic job, guys. Just close out on some simpler questions, I think. Finishing the thoughts on slide 44. So you do identify that you think it's an anomaly, and you have explained why you did what you did with the data. My question there is, based on that, was there any inclination to investigate what may have caused the anomaly? And then from there, was there any desire to test that, to try and get better data?
So looking back, currently all we have is the data from our second wind tunnel test. And while we would love to do a third wind tunnel test, especially with our longitudinal nonlinear region, that just simply isn't available to us with the scope of this course.
Was it a time issue?
Yes.
Were there any theories, though, as to what may have caused that anomaly?
It's believed to be just a data acquisition issue. The way that the LabVIEW software runs is there's a several step process to acquiring data, then writing the data to a file, and if that doesn't happen in the right sequence, or if the software doesn't update as soon as it should, then it could write either, we've seen where it writes the same data from the most previous, you might change angle of attack or beta, and it writes the same data from the previous iteration. That's a little bit easier to pick up on, but something like this is believed to be from a similar issue.
Okay.
Yeah, so with the data acquisition, Evan was running the computer, and you have to hit record, right, when you're at the data point. All it would have taken would be somebody's hand on the knob, ready to go to the next beta angle, and we could have seen that. So that's our right now assumption as to what happened. Another assumption, I should say.
Next question is slide 17B. Notice that you have great flight envelope there for normal conditions at sea level, but what about cruise altitude and gust conditions in non-ideal environments?
So we do have gust conditions at sea level toward the end. There. And we in preliminary design and in previous design reviews during this semester, we have presented on flight envelopes at higher altitudes. And the large difference there is that the stall region compresses and the maximum velocity extends. But I don't have those in a backup slide today.
Okay. Just for future reference, it's probably handy to have that available. My last one is for your cost estimates on 62B. Just looking at the deltas between those two pie graphs, percentages of hours versus percentages of dollars, how did you calculate or estimate the dollar value for the time spent?
Dollar values were calculated using hourly rates that were suggested by the professor as a requirement at the beginning of the course.
Okay. Go ahead, thank you.
Thank you.
So I'm a chemical and materials person. So I did have a question on 15A. Are you at all concerned about the maximum stress there and the margin of safety?
No, I'm not. It's after a factor of safety of 1.5 is applied. It is a thin margin of safety, but it's after that factor of safety. And additionally, there's in calculating the maximum load of takeoff on the horizontal tail, we used our CL max value, which we would not actually deflect to CL max because that's right at the border of the stall region. And so we would have a buffer both on the CL observed by the horizontal tail, and then also there was the applied factor of safety.
Okay, a little clarification on that might have been good, because if you just look at that margin of safety.
It looks way too thin.
Right, exactly. And the other thing that I would just kind of point out, I think it was a couple points when you did have sort of a difference. You're talking about it's close. So slide 33B, I think was one example that I noticed. You talked about the difference there, and then you said it's close. So be careful when you're editorializing. Kind of let the numbers speak for themselves and let the audience decide what's close.
Okay, thank you very much, guys.